In the last video, power cycles were introduced. Today we will look at reciprocating engines, like the ones in your car, assuming it's not electric. These can be approximated by two specific gas power cycles using the standard error assumptions. A reciprocating engine is just a piston cylinder device, just like any gas or diesel powered engine. These are used in cars, planes, and electric power generators. One important parameter for reciprocating engines is the compression ratio, R. This is the ratio of the maximum to minimum volumes inside the cylinder. The minimum volume occurs when the piston is at top dead center, or TDC, while the maximum volume occurs when the piston is at bottom dead center, or BDC. So R equals Vmax over Vmin, or V at bottom dead center over V at top dead center. There are two classifications of reciprocating engines: spark ignition, SI, and compression ignition, CI. Spark ignition engines use a spark plug to ignite the fuel and are characterized by the Otto cycle, while compression ignition engines simply compress the fuel to a temperature over the Otto ignition temperature of the fuel and are modeled using the diesel cycle. We will be analyzing both of these cycles in this video, starting with the Otto cycle. The most common form of the Otto cycle is for the four-stroke internal combustion gasoline engine. As described by its name, there are 4 strokes involved in one complete cycle. Note that this then corresponds to 2 revolutions of the crankshaft for every 1 cycle. The 4 strokes are as follows. The compression stroke: the piston compresses the air-fuel mixture, increasing the pressure and temperature. The power or expansion stroke: as the piston reaches top dead center, the spark plug ignites the air-fuel mixture, causing a further increase in both temperature and pressure, which then pushes the piston back down. This is where work is done, or the power is generated. The exhaust stroke: on its way back up, the piston pushes the combustion products out of the exhaust valves. And finally, the intake stroke: as the piston is on its way back down, more air-fuel mixture is injected into the cylinder, and the cycle begins again. Here is the description in picture form. Piston goes up, compressing the air-fuel mixture. It is then ignited and pushes the piston back down. Then the exhaust gases are removed and more air-fuel mixture is added during the next 2 strokes. We can also see the progress of this real cycle on the PV diagram shown here. This is what is actually happening. It is very hard to analyze in its complete state. It is much easier to analyze using the idealized cycle, which is what the Otto cycle is actually for. In this idealized version, the compression stroke is modeled as an isentropic compression process. The first part of the power stroke, when the gas is ignited, is modeled as a constant volume heat addition process. The second part of the power stroke, as the piston moves back down, is modeled as an isentropic expansion. And at the end of the power stroke is modeled as a constant volume heat rejection process. Note that the exhaust and intake strokes do nothing thermodynamically in this idealized process. Another common internal combustion engine is the 2-stroke engine. In this case, all the processes are combined into just 2 strokes of the piston. As the piston moves down past the exhaust port, the exhaust gases are pushed down, effectively making the exhaust stroke part of the power stroke. As it moves further down, new air-fuel mixture is added and compressed, which then goes into the chamber through an intake port and is further compressed and ignited, making the intake cycle part of both the power and compression cycles, and this completes the cycle. 2-stroke engines are less efficient than 4-stroke engines since the exhaust gases are not completely expelled, while some of the air-fuel mixture gets expelled before being ignited. On the other hand, they are simpler and cheaper than 4-stroke engines, and therefore useful for small engine applications. The Otto cycle is a good approximation for both 2- and 4-stroke engines and is the same for each. It consists of the following 4 internally reversible processes. 1 to 2 is an isentropic compression, 2 to 3 is a constant volume heat addition, 3 to 4 is an isentropic expansion, and 4 to 1 is a constant volume heat rejection process. As indicated earlier, thermodynamically nothing is happening during either the exhaust or intake cycles for the 4-stroke engine in this idealized process. So a better PV diagram is shown here, where 0 to 1 and 1 to 0 represent these final 2 strokes. No heat is added or rejected during either of these two strokes. Additionally, no net work is done over the two strokes. There is some work done on the gas during the exhaust stroke as the volume is changed. However, an equal and opposite amount is then done by the gas during the intake stroke. Therefore, these two cancel out and are essentially irrelevant to the thermodynamic analysis. The only thing of note is that these two strokes take time, and the same amount of time as a cycle approximated by the Otto cycle. Therefore, when calculating the power produced by a four-stroke engine, it is only half of what is calculated through the Otto cycle, since it only consists of two of the four strokes. The Otto cycle is approximated as a closed system, and so the net work is equal to the heat in minus the heat out. And since the two heat transfer processes occur at a constant volume, we have Q in equals U3 minus U2 equals CV times T3 minus T2, and Q out equals U4 minus U1 equals CV times T4 minus T1. The thermal efficiency of the Otto cycle can then begin with the usual A to Otto equals net work over Q in, or 1 minus Q out over Q in, or 1 minus T4 minus T1 over T3 minus T2. Now we know that the processes 1 to 2 and 3 to 4 are both isentropic, so the temperatures can be related to T1 over T2 equals V2 over V1 to the K minus 1 power. Then the volume ratio is the same, bottom dead center to top dead center, and back to BDC. So V2 over V1 is equal to V3 over V4, but V3 over V4 to the K minus 1 power is T4 over T3 due to the isentropic relationships. Therefore, we have that T4 over T1 is equal to T3 over T2. So taking T1 from the numerator and T2 in the denominator in this expression up here, these two terms in the parentheses cancel out, and we simply have 1 minus T1 over T2. However, T1 over T2 equals V2 over V1 to the K minus 1 power, where V1 over V2 is the compression ratio R. So the efficiency ratio of the Otto cycle is A to Otto equals 1 minus 1 over R to the K minus 1 power. From this, it can be seen that the thermal efficiency of the Otto cycle increases as R increases. It will also increase as K increases. This is also the case for real-life spark ignition engines, where typically compression ratios are in the neighborhood of 8 to 11. It can be seen in this graph that this would give efficiencies near 60 to 70%. For air, K equals 1.4, usually the value used for air at normal temperatures anyway. But for other gases, it can be seen that the efficiency also increases as K increases. In real life, the efficiency is usually only about half of this idealized value, around 25 to 30%. This is due to the inherent irreversibilities and other energy-sapping inefficiencies that real life has to offer. Compression ratios higher than around 11 are not seen very often for a few reasons. First, it can be seen that the curve begins to flatten out around this value, so the efficiency is not increased as much for higher values. Second, higher compression ratios lead to higher temperatures. If these temperatures get too high, specifically higher than the auto ignition temperature of the fuel, then the fuel will begin to ignite prematurely, leading to undesirable engine knock. Now we can move on to the second type of engine, compression ignition. The ideal cycle for these types of reciprocating engines is the diesel cycle. In these engines, the combustion is initiated when the fuel's temperature reaches the auto ignition temperature, so no spark plug is needed. The fuel is injected after the air is above this temperature to avoid premature ignition. For this reason, higher compression ratios are possible and are used in diesel engines. Other than this, the only other difference between this cycle and the Otto cycle we just saw is that the combustion process takes longer, meaning the volume is no longer constant. However, the pressure is relatively constant over this interval, and so instead of the constant volume heat addition process in the Otto cycle, we have a constant pressure heat addition process in the diesel cycle. So the diesel cycle consists of the following four internally reversible processes. 1 to 2 is an isentropic compression. 2 to 3 is a constant pressure heat addition process. Again, the only difference to the Otto cycle. 3 to 4 is isentropic expansion, and 4 to 1 is constant volume heat rejection. These are shown here on PV and TS diagrams. Constant pressure constant volume, and isentropic processes. Again, only difference here, heat addition is a constant pressure horizontal line, as opposed to before, it was a constant volume vertical line. Similar to the Otto cycle, the heat out is the same as before and can be written as Q out equals CV times T4 minus T1. But the heat in is now given by Q in equals Cp times T3 minus T2 due to the fact that it is now a constant pressure process as opposed to constant volume, so Cp instead of Cv. So the efficiency of the diesel cycle is given by A to diesel equals 1 minus Q out over Q in equals 1 minus T4 minus T1 over K times T3 minus T2. This is similar to that of the Otto cycle, but now we have this additional factor of K in the denominator. And we can define a cutoff ratio as the ratio of the volumes before and after combustion, Rc equals V3 over V2. For the Otto cycle, it was assumed the entire combustion occurred at V2. For the diesel cycle, it is a slower process, so that is no longer the case. The combustion occurs to some volume V3, then the isentropic expansion begins. Then performing a similar analysis to the one for the Otto cycle, T1 over T2 equals T4 over T3 times Rc to the k minus 1 power. T4 over T1 equals Rc to the k, and T3 over T2 equals Rc. Putting all this together, the efficiency of the diesel cycle then becomes eta diesel equals 1 minus 1 over R to the k minus 1 power. This part is the same as the Otto cycle. But then we have this additional multiplicative factor of Rc to the k minus 1 over k times Rc minus 1. Note the additional factor will always be greater than 1. This term in square brackets. Therefore, the efficiency of the Otto cycle will always be larger than the efficiency of the diesel cycle with the same compression ratio. However, diesel engines generally operate at higher compression ratios than those using the Otto cycle, usually in the range of 12 to 24, which means that the thermal efficiencies of diesel engines are generally higher than those of the Otto cycle in the range of 35 to 50%. When the cutoff ratio is 1, the efficiencies of the Otto cycle and diesel cycle are equal. Note that this actually corresponds to V3 equals V2, which reduces to a constant volume process. One final note on these cycles. These are idealized cycles, where every process is entirely internally reversible. However, the overall process is actually not totally reversible. This is because they involve heat transfer over a temperature difference during both the heat addition and rejection processes, which are irreversible. This results in the efficiency of both Otto and diesel cycles being less than that of the Carnot cycle using the same temperature limits. So that is it for today. Here's the usual pre-lecture example and answer. If you have any questions, feel free to ask during lecture.